Hello, folks. So, this is some grade A bullshit that we're not here today in class, but, it is what it is, so we'll get on with our lecture. We'll figure out, figure out the order of labs and whatnot, but we'll plan on doing the air quality or working on some of that for Friday. Maybe if you can get some water sample before then, we can do some water sample because the air quality one, part of the setup won't take that long. But you need a water bottle to collect your water sample in before then, so hopefully I can get that to you on Monday if you haven't already picked yours up. But we'll go ahead and continue with our PowerPoint. So, talking about that. How does acid rain get formed? Most common form, which is our nitric acid. So, nitric acid rain always begins with our nitrogen oxide samples. So, the majority of is a conversion of atmospheric nitrogen via the internal combustion engine. So, most of it's coming from our cars, as we get already seen. Same thing in the smog. Though there are some other sources, including organic compounds and wood-based fuels, and some are a byproduct of microbial nitrification in the soil. So we cannot avoid this even if there was no more oil to mine. We run out of fuel for cars, we would still have some acid rain, just a whole heck of a lot less. Even lightning will serve as a minor source. Now, nitric oxide will be oxidized by oxygen, by ozone, by hydroxyl radicals, by peroxy radicals, all of this to get us to where we'll eventually need to be. So some of the same reactions we saw in smog will play a part here. Like NO will form NO2 in the presence of ozone. That's one of our big ones. This nitrogen dioxide will contribute to ozone and hydroxyl radical production, as we saw last chapter. And the NO is regenerated in the cycle, then keeps it going. So the NOx doesn't get removed from that cycle. The NOx will eventually get removed from that cycle, but that's in the form of acid rain. That if NO2 hits a hydroxyl radical and a third body, it will form nitric acid. So it's one of those like removal mechanisms that when we get enough OH and enough NO2 and an NO2s get not able to be used in other ways, it removes it from there. If you have a buildup of too much of these radicals, it forms nitric acid. So this, we will see a second order rate constant of 2 times 10 to the negative 11th times the temperature divided by 298 raised to the power of 1.6. So meaning the hotter it is, it's a temperature dependent. Let's see. Hotter it is, what would that do? Like if I had 500 degrees divided by 298 raised to the power of 1.6.43. 1 divided by. So the hotter it is, the slower this process is going to proceed. The colder it is, the faster this process can proceed. That is basically if the molecules have too much energy, they're not going to stick together. Now, due to the starting materials, NO2 and OH being byproducts of photochemical reactions, they get used up and go in there. This process will occur chiefly in daytime. So this OH radical and NO2 radical, the reaction occurs at the daytime. So hypothetically, what would the rate of this be if at 20 degrees C? What would the half-life of NO2 be at 20 degrees Celsius. The half-life is the ln2 of over K1 of our first order reaction. K1 is K2 times OH. So at 293, you can plug that in, figure out what is K2, and multiply by your essentially constant concentration of OH, and plug some things in, largely at 20 degrees C at a more or less constant concentration of OH radical. The half-life is about 7.8 hours. That's a lot of complicated math, but we're waving our hands for the most part right here. Now, however, once sunset happens, we get a different mechanism. So we can no longer have a high concentration of OH radicals, so ozone has a chance to build up, because ozone would be zapped normally in the daylight. So this one, while this mechanism can technically occur during the daytime, it's chiefly favored at nighttime, because otherwise, as I said, the competing ozone being zapped by light. So ozone hits NO2 and we form NO3. This nitrate radical, it's not really a nitrate. It's a nitrogen trioxide, really. But this nitrogen trioxide, they often call it nitrate. The nitrogen trioxide can react with nitrogen dioxide to form nitrogen monoxide and oxygen. And it can also, the nitrogen monoxide reacts with nitrate. It can form nitro, the nitrogen dioxide. So we can get a bunch of mixture of different products with this. So the NO2 essentially is decomposing our ozone. Decomposing our ozone and giving us a variety of mixtures of NO2s and NOs. But similar to the OH radical, NO3 radical can also add across double bonds to form nitrate radicals. So this radical production is then susceptible to many further reactions, including some oxidations. So nitrate can also react with our aldehydes. And so when it reacts with an aldehyde, it can steal hydrogen to form nitric acid from our aldehyde. And it can steal a hydrogen from our hydrocarbons, our VOCs, to form nitric acid. So nitrate, the nitrogen trioxide radical, is a very reactive radical, as we can see by all these other reactions that it can do. It can react with NO2, it can react with NO, it can react with aldehydes, it can react with hydrocarbons. But the nitric acid is one of those terminal products. Yeah, and of course those alkyl radicals can undergo further reactions with dioxygen, as we saw. Now another kinetically fast set of paired reactions can occur. If nitrate bumps into NO2, it can also form N2O5 instead of cleaving off oxygen. And if the N2O5 mixes in with some peroxide, hydrogen peroxide, it can form nitric acid. So we have some peroxide, hydrogen peroxide, as a byproduct of some of these reactions. We have these peroxy radicals. So a small fraction of the NOx can also be removed through the formation of PAN, if you remember. The peroxy acid hydrocarbons can react with nitrate to form PAN. That can also remove our nitrites, our NOx. But once we form nitric acid, when we form nitric acid, this doesn't react any further. It stays in the atmosphere until it's either removed through a wet or dry deposition. So until it reacts with the water and gets absorbed and dissolved in water, or it's binding to particulates in the atmosphere that can settle onto things. So it's going to remove this from the atmosphere and put it into our water and soil. This nitric acid that's formed in this complex process is the main contributor to acid rain. Now, this nitric acid can react with ammonia, whether this is from nitrogen fertilizers or from urea and animal urine or other reduced nitrogen sources to form ammonium nitrate. Ammonium nitrate can actually be a seed, a condensation nucleus, which water droplets can form. So when you seed water droplets actually form around tiny suspended particulates in the air. So crystals, small little particles of dirt is where a rain droplet starts to form. It lowers the energy of the water droplets sticking. Once they start to stick, they build up and build up and build up until it's a heavy water droplet. It's the same idea where we talk about seeding clouds to make it rain. You're dropping molecules into the chemicals into the cloud that encourages the water droplets to accumulate on these molecules that then causes it to build up, so the density is so high that they start to fall. Precipitation occurs. So this ammonium nitrate, if it's not rained out, can also be deposited as just a solid aerosol, solid dust particle that can just land when there's not enough wind and breeze to keep it in the atmosphere. So now, sulfuric acid is a little bit more complicated than nitric acid. And it's like, well, that was already complicated. But it's still, we already know many of the reactions that nitrate and NOx undergo. So these are kind of new. So problem with sulfur is it often comes from a whole variety of sources. So various different sulfur compounds that are partially oxidized, and they can all have different sources. So hydrogen sulfide, which is just the water, it's the equivalent of water, but with sulfur. Carbon sulfide, which is a mixed version of CO2, a partially oxidized version. Carbon disulfide, which is the sulfur version of CO2. Methyl mercaptan, which is the sulfur version of methanol. Dimethyl sulfide, which is the sulfur version of dimethyl ether. And dimethyl disulfide, which is the sulfur version of a peroxide. But all of these compounds, regardless, have sulfur with an oxidation of -2. Sulfur is a lot more stable in the disulfide. I guess the disulfide is not -2, but that's the only case where that's not the case. But it's often released from the oceans and from the soil by various microbial processes that are under reducing conditions. Reducing gets them less positive, more negative. Gives sulfur to some of its more negative sources. Warm temperatures will also increase the rate of these production of molecules. But the main idea is all of these can form thionyl radicals by one form or another. So it's just they need to bump into a hydroxyl radical. So if you have a hydroxyl radical and the hydrogen sulfide, it forms an SH in water. If you have a hydroxyl radical and a carbonyl sulfide, it replaces the sulfur with the oxygen. It forms CO2 and SH. If you have a carbon disulfide and it hits hydroxyl, it replaces one of the sulfurs with the oxygen and forms the carbonyl sulfide and forms SH. The hydrogen sulfide and carbon disulfide react quickly. However, that COS is relatively stable and a lot slower to react. So that one is kind of a slow spot. But these initial twos are pretty fast. Now the thionyl radical can lead to the formation of sulfur dioxide. So SH radical hits oxygen to form sulfur monoxide, or the S and a hydroxyl radical, which then can speed up more SH radicals. SH radical can bump into ozone to form it would be essentially sulfur aldehyde, essentially S double bond O H radical. And oxygen and SHO radical can react with oxygen to form SO as well. So whether it's oxygen or ozone, they form SOs, and you form new radicals, the proxy radical or the hydroxy radical. Then SO can either react with oxygen or ozone or nitro groups to form SO2. So if it reacts with oxygen, it forms monooxygen. If it reacts with ozone, it forms just regular oxygen. If it reacts with NO2, it forms NO. So it can react through a variety of different mechanisms, but the net goal is to get SO2. Now, how do we get these sulfur compounds? It's largely coming from things like phytoplankton. They produce a large amount of dimethylsulfonylpropionate, DMSP, which will be degraded to form our dimethyl sulfide via algal or bacterial processes. So the plant plankton produces a big complicated sulfur molecule that decomposes and gets degraded through digestion to DMS. Only a small portion of this DMS does find its way into the atmosphere, but in quantity, it is the most important sources of sulfur because we have so much phytoplankton, even though not a lot of it that gets produced by a phytoplankton finds its way into the atmosphere because you just have quantity. You have so much phytoplankton that even if only 1% of it's produced finds its way into the atmosphere, 1% is enough. Things like algal blooms can increase this. So when we have giant blooms of algae because of pollution, it's going to produce a lot more DMS, which is going to a lot more acid rain. The dimethyl sulfide can react with hydroxyl to oxidize to dimethyl sulfoxide and methyl sulfonic acid, but this mechanism isn't fully understood. So the dimethyl sulfide right here, it's going to form either this guy or this guy and then some sort of complicated oxidation products. But the main product of this dimethyl sulfide is SO2, which will ultimately produce sulfuric acid. So the main thing is we have a lot of complicated reactions that are just forming SO2. However, SO2 can often be formed by diesel fuels, by ore smelting, by anything burning of anything with sulfur directly in it. So we don't have to wait on nature to take its course. We can get SO2 by human means as well. All that's pretty straightforward. But now here's where it gets a little bit more complicated. That we can have both a series of oxidative homogeneous reactions or oxidative heterogeneous reactions. Homogeneous reactions are reactions that... Sorry, I gotta sneeze. Are reactions that take place in solution. Heterogeneous reactions that we'll talk about are ones that take place on the surface of a solid aerosol. So it all depends on how the sulfur dioxide is reacting with the atmosphere. So homogeneous reactions can take place as a gas or in a solution. But this process takes place by at least two distinct sets of processes. The first one is homogeneous gas phase. So the rate determining step is SO2 has to hit a hydroxyl radical and a third body just to shake off some of the energy. And so the hydroxyl radical can stick to form HOSO2 radical. Now, at lower troposphere, the reaction is a pseudo second order, meaning the third body M is essentially ignored because we have a lot of concentrations of nitrogens and oxygen. But in the upper atmosphere, the rate should technically go down. But because the activation energy is negative, so the lower temperature of the upper troposphere actually increases the rate slightly. So it actually has too much energy, which is why it needs that third body. So when it's actually colder up there, it slows the molecules down so they don't need to shake off as much energy with that third body. So we see like an inversion here. So looking at the bottom, the temperature with relation to altitude, that it drops drastically in the first 10 kilometers, and then it kind of levels off and slowly starts to creep back up from 30 kilometers up to 50. And if you're just looking based on the pressure, the pressure should be this line. But what we see is closer to the surface, it's slow as we get up to from the troposphere to the stratosphere. It actually increases, and then it starts to decrease, but it doesn't decrease in a linear fashion. It actually peaks out here. It peaks out here where the temperature is actually kind of at its lowest. And then it creeps back down as the temperature picks back up. So we don't see a direct, it's not quite a linear drop that you would expect based on the pressure. Now, HSO2 radical can undergo a series of rapid reactions. It can bump into oxygen to form a proxy radical in sulfur trioxide. Sulfur trioxide can then bind to water to form sulfuric acid. This hydroperoxy radical can actually contribute to nitric acid formation because, remember, NO plus hydroperoxy forms NO2, and NO2 plus the hydroxy radical can form nitric acid. However, some of this hydroxyl radicals can instead react with sulfur dioxide so in the process of forming sulfuric acid, we can either catalyze nitric acid formation or catalyze more sulfur dioxide reaction. So you can either form more sulfuric acid or more nitric acid depending on what we have more of, more NOs or more NO2s or more sulfurs. The SO2 can also react with monooxygen to form sulfur trioxide. But under the tropospheric conditions, the monooxygen is so low that it doesn't really contribute by much. Now, the other mechanism is a heterogeneous reaction. So it means we're having gas phase reacting with a different phase, in this case, aqueous phase. So we will look at these reactions during the polar spring and the polar stratospheric clouds. That's when we first saw this. That first, SO2 in a well-mixed gas dissolves into water droplets. And that's controlled by the pressure. The water droplets, the SO2, can form hydrogen sulfite and acid. They become acidic. And that's controlled by a Ka constant, the equilibrium constant. And the sulfur trioxide can further react with more water to form sulfite with another Ka constant. So the sulfur dioxide is reacting in these ways that acidifies the water. It's still not sulfuric acid, but it is slightly acidic. And of course, the solubility of SO2 increases when you have something that removes this hydronium, with something that removes this H3O+. Things that remove this is going to make the reaction go more to the right. So solubility increases if the rainwater is neutral or slightly basic. So the solubility of SO2 is just one factor that will affect the rate of these reactions. If SO2 can't dissolve very much, this reaction will not be a major factor. But some of these guys will also be oxidized by hydrogen peroxide. It's another source for the production of sulfuric acid, while the concentration of hydrogen peroxide is rather low compared to SO2's, 1 to 2 parts per billion by volume, compared to sulfur dioxide's 10. It has a much higher water solubility. So the hydrogen peroxide that gets produced is largely dissolved in the water. And so if it runs into the hydrogen sulfite, it oxidizes into peroxy hydrogen sulfite. And this hydrogen peroxy sulfite can rearrange into hydrogen sulfate. So I'm just showing you what the structure of these look like. The hydrogen hydroperoxy sulfite looks like the left structure. It rearranges, moving an oxygen over to form the hydrogen sulfate, as you see there. The hydrogen sulfate can then be protonated to form sulfuric acid, and that's going to so this process can be increased by the acidic concentrations, and it's going to keep that as that structure. So, looking at the speed of this. So, the formation of sulfuric acid, in this case, is a function of K2 and the acid concentration and the hydrogen peroxy sulfite. But since the hydrogen peroxy sulfite is usually in low concentration, we need to determine this in terms of its most stable reactants using steady state approximation. Now, in kinetics, I may have briefly talked about this, but the idea of steady state approximation says if an intermediate is significantly low and it reacts quickly enough, it essentially builds up. We can look at the rate of its formation and the rate of production, that its change in concentration essentially is zero. And so if we set the rate of this to be zero, we can look at it entirely in terms of how it can be formed and how it can be consumed. K1 is how it's formed, one of the ways it's formed. K minus 1 is the reversible reaction of it breaking apart back into its original products. And K2 right here is how it can be consumed in this second step. Now, solving for the concentration of HOOSO2 minus. So we'd get those to the other side where that'd be 0. And divide by, and essentially, and solve this in terms of HOOSO2. Now, technically, if we go back one, this reaction actually has water as a byproduct, so it should not be just this by itself. However, water is usually in such a great concentration that we don't need, it's essentially pseudo first order because it's done on rain droplets, an aqueous solution essentially. So we don't need to calculate the water concentration. So what does this mean? So when we isolated this on one side, solving for the hydrogen peroxysulfite, we get hydrogen peroxysulfite concentration is equal to this complicated function. Plugging that back into the original concentration, it's a very, very complicated function, but there's certain parts that we can look at. So looking at K1, K2, HSO3 minus, H2O2, hydronium over K minus 1 plus K2 times hydronium. So looking at that, breaking it down, K1, K2, and K minus 1 are known. So basically, what happens if the pH, so the concentration of hydronium is significantly high, if the pH is low, so the concentration of hydronium is high, in this case, it's more if pH is greater than 2. If pH is greater than 2, so it's not super acidic, then the rate of K minus 1 is the major factor. And this guy rounds out. And so if the pH is not super acidic, the equation simplifies to this. All this is a constant at a given temperature. It's a 3-body process. And you can figure out some of those guys in terms of Ka. So really, it simplifies down to this. So when pH is greater than 2, it becomes a crap ton of constants times the hydrogen peroxide and the pressure of SO2. It's essentially that when it's not super acidic, you can look at this rate as a function of SO2 concentration and hydrogen peroxide. Though below 2, it gets a little different. So this function works pretty well when pHs are between 2 and 5, when the hydrogen sulfite is the dominant species. So, and it largely becomes pH independent. However, below pH 2, the rate will decrease due to there's a change in the denominator. So if hydronium is greater, these things can actually cancel out and things get a little complicated. So there's a change in the denominator, and so it becomes just hydrogen sulfite and peroxide, and gets a little complicated. At higher pH, HSO3 concentration goes down because we deprotonate that into SO3 2-. And the SO3 2- will not be oxidized by hydrogen peroxide. And there is another reaction where ozone can react with these in heterogeneous solutions, but only below pH 5. But in these slightly acidic conditions, it's not a significant reaction. So we don't have to worry. That one isn't a major contributing factor. But basically, we can oxidize this. So to summarize this, we have some sort of sulfur compound. The sulfur compound reacts with hydroxyls eventually to form sulfur dioxide. If it's just in the gas phase, it can react with more hydroxyl radicals to form sulfur trioxide and water, and sulfur trioxide reacts with water to form sulfuric acid. If the sulfur dioxide dissolves into water droplets, it can react with hydrogen peroxide or ozone to form sulfuric acid in the presence of clouds, mist, rain, or snow. Either way, we're forming sulfuric acid. Even oxygen can react in this way, but this is much more slow, and so it's not a contributing factor. However, certain things like certain metals that are soluble in the water at low pHs can catalyze these reactions. So iron 2 and iron 3, manganese 2, copper 2, and cobalt 3, if they're dissolved and they form aerosols in the water droplets, can speed up these oxidation processes. However, at higher pH, these metals can precipitate and form solids. And these solids can also catalyze these reactions by just providing a surface. So sometimes reactions form better along surfaces rather than trying to float around and bump into each other. So these metals, when they get into the atmosphere, can catalyze them either in solid or aqueous form. Now, one last slide or so, I think. Removal of atmospheric sulfur. So sulfuric acid then largely dissolves into our cloud water droplets and can be rained out or washed out. It can also react with ammonia, same way as nitric acid, to form atmospheric aerosol condensation points for water vapor. So it can react in a 1-to-1 ratio to be partially neutralized, or a 2-to-1 ratio to be completely neutralized. So these reactions will neutralize some of the acid, but usually acid concentrations are much higher than our ammonia concentrations. So the acid is rarely neutralized in this way. Now, another method of removal is the formation of that OCS, that carbonyl sulfide, which we said was a little bit more stable. They can still react with hydroxyl radical, but it's so stable that it lasts between a half year to 7 years. So this can even diffuse into the stratosphere, where it can be converted into sulfate ions, and then be an important part of their stratospheric aerosol clouds that we talked about in the polar vortex. But I think that's where I'm going to stop for now. Let's see. Yeah, I'll go ahead and stop there. Now, in the future, I want you to kind of have some homework done. I'm going to try to look at some of your homework next week. So try to have some homework done, and we'll talk about that on Monday. Have a good day.